Thank you. Welcome everyone. I'm very excited to host the Washington Statistical Society's Presidents, and yes, that is S apostrophe, invited lecture that is co-hosted by NASS Research and Development Division seminar series. So we're very excited today to have Rebecca Sturtz to present to us. And I wanted to say a few words about her before we get started. So I'm not going to read the abstract that was presented in the invitation, but just to say a few words. So Rebecca is an assistant professor in the Department of Statistical Science at Duke University. And I say that with a smile because I am a UNC Chapel Hill graduate. So saying that with all affections. So Rebecca wears a lot of hats in addition to being a principal statistician at the US Census Bureau. So she is a recognized expert on record linkage and small area estimation amongst other topics. And so we'll get a flavor of her research on that today. So I also wanted to say that she is a well-renowned instructor, but also a mentor for young statisticians. And so she's advancing not only the science, but also the careers of other individuals in our area. And so it is with great pleasure that I pass the microphone over to Rebecca for our seminar.
Thank you so much, Jill. I'd just like to thank the Washington Statistical Society as well as NASS for this great honor in giving this lecture. Let me just share my screen and go to full screen. I'm happy to take questions along the way. If anyone has a question, if you could just let me know who you are. I like questions. I like them very much. So what I'm going to talk about today is my main research, as Jill said, was on entity resolution. I'm going to talk about broadly the scope of the problem and a lot of different problems that I've worked on with societal impacts in either survey methodology, in statistical science, or machine learning, or in all of these aspects. My work has been supported by NSF through my career award and some other another collaborative award, as well as the Sloan Foundation. So I'd like to thank them. This work would not be possible without numerous collaborators, PhD students, postdoctoral fellows, former postdoctoral fellows, other faculty I've collaborated with. And so I'll highlight the work that I've done with them, but I'd like to thank them for working with them and collaborating with them over the years. So entity resolution is a problem that appears in many, many different aspects. It appears in medical data, it appears in survey data, such as decennial census data. It appears in human rights statistics applications, and it's appearing more in industry as a society, we collect more and more different types of data. And as I go through my talk, I'll highlight different applications and case studies that I've worked on. So you might be wondering, what do these data sets have in common? So there's duplication in the data, and specifically what I'll talk about is the amount of duplication is typically small. And before we can actually apply any inferential or prediction methods, as we do as statisticians, any duplicate records must be removed. And so a large question that we look at in entity resolution or record linkage is how should we remove these duplications so that we can do these inferential and predictive analyses in a sensible way. So I like to showcase what I think of as what's known as the data cleaning pipeline. And so as you'll see, entity resolution is the third stage, and it's just one part of a giant pipeline where you start out with survey statisticians collecting all of this different data. And then the schema has to be aligned. So there has to be some data cleaning process. And then typically the data is too large. We have to end up doing at least n-squared comparisons. And so we have to do some type of dimension reduction. And we have to do these two steps in order to actually remove duplicate entities so that we can understand which records will refer to the same entity. And then finally, in entity resolution, we'll end up with clusters of records. And so in the canonicalization or merging or data fusion step, we'll actually merge records that refer to the same entity. And then we can finally end up with integrated data where we can actually perform a logistic regression or a simple linear regression. So as you can see, the process is quite complex, and entity resolution is just one step of this task. So as I mentioned, entity resolution is the process of merging together what are usually very noisy. They are structured databases to remove duplicate entities, and often they're in the absence of a unique identifier. Of course, if I have a unique identifier, the problem's pretty much solved, and I can call it a day and go home. There's a lot of other names that are used for entity resolution. Some of them are called record linkage, de-duplication, duplicate detection, data matching, data integration, and data cleansing. So I'm going to start out by going through some of the foundations and terminology in case you're not familiar with the literature. And then I'll go on and talk about the history and how record linkage became very prevalent. And then I'll talk about some of the work that my research group has done on this area. So I like to think of record linkage as a graph with no edges. So we have different features. So a node is a particular record, and each record has information behind it. Now, what we're trying to do is figure out if this record is the same as the other records. So for example, most people call me Becca, and this is my last name. And so, but a lot of people will call me by my first name if they're a family member. So for example, my mother would call me Rebecca. And so these two records are thought to be co-referent, especially if I go behind the attributes and look to see at the address information, for example. However, a lot of people don't actually realize that my mother's name is also Rebecca, which is incredibly confusing. So this might be, if you don't know me very well, you might think that someone might call me Becky. And so this would be an instance of two records that you would have to figure out if they're co-referent or non-co-referent, or rather a match or not a match. And so if we look at this entire space, when we started out doing record linkage procedures, we needed to figure out, we had to do all-to-all comparisons. And what we've moved away from is moving away from those all-to-all comparisons such that we can speed up the process dramatically. Now, what does this really look like? What's behind this graph? Well, entities are real people, or they're objects or businesses, or they're tangible things. So this node is a representation of myself in a real point in time that can change. And this is my physical address that I can find on a Duke web page and scrape. And then if I try and find something about the other Rebecca Sturtz or Becky Sturtz, I can find information in West Virginia, and perhaps the phone number is blanked out, and then I encounter some missing data. And so what I would try and do here is I would want to find a record linkage or entity resolution algorithm that would tell me if this is a match or a non-match. Now, more specifically, the goal of entity resolution is actually to provide clusters of records that are the same. So in a simplistic sense, this is going to be a cluster of size 2, where I think that these records are a match and they're the same. And I've ruled out other records. Now, I could certainly have clusters that are larger, but we tend to end up with clusters that are small. Now, you might have noticed that I haven't identified that this record or this record is more representative of me as a person. And in order to move through into the data cleaning process, in order to find the most representative record after entity resolution, we have to go to the last stage of the data cleansing process, which is canonicalization, data fusion, or merging. And this means I have to find the most representative record. The easiest way to do this is to simply choose one uniformly at random. There's many other approaches to deal with this task in a more sophisticated way, but I won't talk about that in the scope of this talk. So again, the last stage would be resolving the records using canonicalization, but for the purpose of this talk, I'm just going to focus on entity resolution, which is an entire field in itself. These are some references if you're interested in looking at the entire space of entity resolution or the data cleaning pipeline moving forward. So before I go into the history, I'm going to talk about just a few challenges that we face when we look at this problem and why it's so difficult. And I like to think about 4 of them. So the first one is the fact that it's very costly to manually label data. So there's vast amounts of manually labeled data, but unfortunately they typically require a lot of time, a lot of money. It's not clear the best way to label such data. And these are always, this type of manually labeled data is required for supervised learning and evaluation. And so the fact that if we need a lot of manually labeled data, this will motivate my approach for using a fully unsupervised approach for entity resolution. Another common problem is scalability. So I mentioned that the entire space, if we're doing all-to-all comparisons, is n squared if n is the total number of records, and we have 2 databases. And this requires approximations to be required to avoid a quadratic scaling. And we also want to try and ensure the impact in adding some computational scalability on our accuracy is minimal. The third issue that we also think about is there's a limited treatment of uncertainty quantification. So as an example, we want to try and make sure that we're able to ascertain the uncertainty quantification of the entity resolution process when we're thinking about building sensible and robust models. And then finally, one thing that hasn't been carefully thought about prior in the literature is it has to do with unreliable evaluation. So standard evaluation methods in the past were known to return very imprecise estimates regarding performance. It's very difficult to tune them, and they are very sensitive to thresholds. And so I'll get into that a little bit when I get into the history more. So I'd like to talk about the history of probabilistic record linkage. I'm going to skip over the details of deterministic methods, but I'm happy to answer questions if you're familiar with record linkage and talk about those at the end. So to my knowledge, the first published work in this area, I think this is incredibly interesting. This paper, it's by Halbert Dunn. He was the chief of the National Office of Vital Statistics in Washington, D.C. So he held this position from 35 to 60, and he was one of the leading figures in establishing a national vital statistics system in the United States. And what he did is he thought about record linkage as a task of assembling together all the important pieces of information which refer to the same individual. So specifically, the way he thought about it is that everyone has a book of life as they are born and when they pass away. And if we think about this, what he was thinking about is how the census, in my mind, works. You start with your life and the information, and you have different, temporal information that is made up of these different records. And we collect this information, and we have to figure out how to make sense of it. So this work led to 2 major advancements in record linkage. The first one was by Newcomb, Kennedy, Oxford, and James in 1959, which was published in Science. And this was the first automated probabilistic method linking historical records. So specifically what they did is they proposed a probabilistic record linkage method, and they implemented it on the state-of-the-art computer at the time, which was the Datatron 205. And I love showing this to my students because they have trouble comprehending what a computer looked like in this day and age and how different they look now. And this was very fast at the time, so it could process records very quickly. Of course, those would be very slow today. So this paper led to one of the, to my mind, the most seminal paper in statistics and survey methodology, which is the Foley and Sunter method of 1969, which appeared in JASA Theory and Methods. And this is the theory for record linkage. And specifically what Foley and Sunter did is they formalized the method by Newcomb and others from 59 in a fully decision theoretic framework. They actually proposed two types of methods in this paper. And the one that is used more today determines if two records are a match using a likelihood ratio test or a hypothesis test. And they decide if it's a match if it exceeds a particular threshold. And many, many, many advancements have been made to the original paper by many authors. However, for the rest of the talk, I'm going to focus on more modern approaches that are known as graphical entity resolution or fully unsupervised that my group has worked on. But this is a very active area of research and has been utilized by Mauricio Sedinle, by Ted Admirando, and a lot of by Partha Lahiri and a lot of outstanding statisticians that have really pushed this to the limits. So I'm going to focus on graphical entity resolution. And the reason I'm going to move away from Foley and Sunter is because typically you can only work with two databases. It's very difficult to extend to higher than more than two databases. It doesn't handle transitive closures easily. It's very sensitive to that threshold for this likelihood ratio test that I talked about. It's also very difficult to prove any theoretical properties for record linkage. And so this has motivated what I call graphical entity resolution. And so I'm going to build off work by Copus and Hilton from 2011 and by Tancredi and Liceo also, sorry, this should say 2001, and from Tancredi and Liceo from 2011. And so this has led to a paper that I led in 2014 that appeared in AI Stats, a paper that I led that appeared in JASA in 2016, and a paper that I soloed in 2015 that appeared in Bayesian Analysis. So the idea of this is we have any type of general records here. So I is indexing any general number of databases, J is indexing the number of records within the database, and L is the number of overlapping features. And what I'm going to do is I'm going to cluster the records to a hypothesized latent entity. So this would be the information that's the true information about the person if we actually knew it, but we don't know it. So we're going to generate this from some distribution. And this data here can be categorical or textual. So it's quite general. And then this lambda here is keeping track of matches and non-matches, and it's known as the linkage structure, the coreference matrix. Now, we're assuming that the data is quite noisy. It has transcription errors, all kinds of noise, and that's coming in through the Z structure. Now that's being tuned by other hyperparameters and more hyperparameters on this parameter. Now, let's assume that X is categorical, then it's going to have a parameter theta L for each field value, and I can tune it this way. If it's a textual field value, then I can put a distribution on that. So again, I can build very flexible, very general models just from this simple construction and come up with even larger, fancier graphical models. Now, if you might ask, well, why did you take this approach and what are the benefits? Well, it handles any number of databases simultaneously. So if you think to the picture that I showed before, it handles that any number of databases, any number of records all in one shot. It handles both categorical and textual data. It handles missing data. Uncertainty quantification is natural under the Bayesian paradigm. Transitive closures are nearly free, so we can always handle transitive closures, and we do this through decision theory. It has very sound theoretical properties, which I'll get to a little bit later in the talk. It generalizes to a wide variety of applications, which I will highlight a little bit later in my talk. It has equivalent or better performance than alternative methods. And all software that we've developed is open source and freely available to nonprofits. And I have links to software at the very end of my talk in case you're interested in looking at it. So putting this in a different way for the graphical model. So again, here's the graphical model. So what I'm really doing is I'm taking the records, the X's, and I'm clustering them to this hypothesized latent entity, Y. So here I'm representing it as a B. It could be anything. So the actual labeling doesn't matter. And then these black edges are representing the linkage structure. So in this step, if I think of this as one iteration of the Gibbs sampler, I'm thinking about this as saying, well, these three Rebecca/Becca Sturtzes all correspond to this latent entity. And so I have a cluster of size 3. Now I'm going to try and separate out the Ryan Tibshranis from the Robert Tibshranis. And so I'm clustering the Robert Tibshranis here to a latent entity R. So here I have a cluster of size 2, and I'm going to do this for each Gibbs iteration and all Gibbs iterations until I haven't failed to converge. And so this is a simple type of Gibbs sampler. Of course, we would do speed ups in order to speed up the Gibbs sampler because we're in a very high dimensional space in terms of the linkage structure. Any questions so far about the setup, the approach, before I get into some applications and papers that I've worked on? Okay, so this is one of the first papers that I worked on, which appeared in JASA. And this is where we ended up removing duplications of a longitudinal medical data set from the National Longitudinal Long-Term Survey, which is from Duke. And this data set is around 60,000 total records before removing the duplicate entities. And what I'm showing you here is the fully unsupervised algorithm. So the green clusters are what the algorithm thinks are matches, and the red ones are what we think are non-matches, where the red ones we would send to clerical review. And you can see that they all satisfy transitive closures. So for example, this one right here is a cluster of size 3. This is a cluster of size 2. I have a cluster of size 5 over here. And so visually, this is very appealing to individuals that might not understand the statistics behind it. And more than that, I can put a posterior probability on the fact that this cluster here actually matches. Now, I talked about how there's theoretical properties behind supporting the methods. So specifically in a paper in AI stats, what I proved is that there are tight performance bounds for these methods. So this is a simulation study illustrating how tight or loose the bounds are. So in the left panel over here, for every time we vary all of the parameters of the model, we can see that for the categorical data, when we look at the Gibbs sampler compared to the true bounds, the bounds are actually very loose. And this isn't surprising. And the reason it's not surprising is because the data on the left are all categorical. Now, if we compare this on the right, here we have at least one string feature, and we can see the bounds are suddenly much, much, much tighter. And so this says something pretty obvious, which says that if you add at least one string feature, your record linkage strength or ability to match is going to improve dramatically, as opposed to in the left-hand case over here. And to my knowledge, you can only prove these bounds for the type of latent model class that you have here. Now, the next thing that I'd like to talk about is scaling. So for a long time, our methods did not scale well. And so one goal was working on scaling Bayesian entity resolution methods to millions of records. But at the same time, we didn't want to sacrifice accuracy and provide uncertainty of the entity resolution task. And this proved to be incredibly difficult. And so this is work that I did jointly with Neil Marchant, who just completed his PhD. And he's at the University of Melbourne, and I co-advised him with Ben Rubenstein. And what we did in this paper is we proposed, to our knowledge, the first scalable joint Bayesian model for blocking and performing entity resolution. And in this approach, the error from this joint task is measured exactly. So you might be wondering, what is blocking? Well, blocking is where we do dimension reduction when we start with the original data. So if I go back to this step here, so blocking is where we place similar records into partitions or bins. So it does a type of dimension reduction. And the type of blocking that we do in our paper, we don't block the records, we actually block the latent entities here, the Ys. And we do that in order that we can use a partially collapsed skip sampler. So I'm just going to show some highlights from our paper. I'm not going to go through the entire model, but I'm going to show you how it works, how well it works, and show some case studies on it. So this is a comparison in terms of the convergence rates for a paper on the left that I worked on in 2015 that appeared in Bayesian analysis, where the method is called Blink and it's on CRAN, compared to our method, which we call de-blink. So if I look here on the left, I'm looking at the convergence rate, which is in red for Blink. So after 11 hours, it fails to converge. And for our method, it reaches convergence almost immediately, where I'm seeing convergence in air quotes here. We can also break this up into the aggregate distortion in terms of looking at the convergence rates for each method in terms of the birth date, birth month, birth year, first name, and last name. And we can see again that for Blink, it's failing to converge, but for our method, it's reaching stability in terms of this diagnostic mechanism basically immediately. The next kind of case study that we looked at is we looked at lots of different types of real and also synthetic data sets. So, and they're quite large. So these data sets range from, this is 60,000 records, this is 600,000 roughly, and this is also around 600,000. This is a synthetic data set, this is a real data set, and this is a real data set. And what we did here is we simply looked at pairwise metrics in terms of precision recall, or you could translate these into the false negative rate and false positive rate. And we looked at a combination of these, which is known as the F1 score. They perform on par, roughly about the same, if not better than the other methods, where we're comparing them to Follagy-Sunter. And one thing I'd just like to highlight is we're giving Follagy-Sunter training data, so the comparison is not completely fair because we're not providing our method any training data. One thing we're able to compute that Follagy-Sunter type methods can't compute is we're able to look at credible intervals, confidence intervals. We're able to look at how much error is actually in the point estimate. So as an example, this is a fully categorical data set from 2 years on the health and well-being of individuals in Italy. And as you can see, it has about 30% error in it. And this is quite expected given the type of data, because many individuals have almost exactly the same information. And so this result is not surprising. And it's nice to be able to see that this aligns and be able to look at the percentage error. Whereas if we tried, we wouldn't be able to ever do this for the fully center method or a non-Bayesian method. We can also do this for this synthetic data set, which is available in CRAN, which is called RL Data 10,000. It's not quite as noisy, but it has some noise in it, and 10% is something that we would expect. The National Long-Term Care Survey, this is a longitudinal data set, which has been anonymized, so we expect it to have some amount of error. Now, if we go to this voter registration data set and the synthetic data set from the Australian Bureau of Statistics, these are quite noise-free because they have so much textual information. And so we expect, because of how our model was built and how generative it is, we expect that it shouldn't have too much error in it. Now, the one thing we still need to improve upon is the fact that our credible intervals are incredibly sharp. And this is consistent with something that I proved in my 2016 paper that appeared in JASA. And this has been improved upon in further work that just is about to appear in JASA with Giacomo Zanella and Brenda Benacourt. And we're still working on ways to scale that up and improve it. But there's a balance, there's a trade-off in terms of scaling and also just building these very complex generative models. So finally, I'd like to highlight some work that I did when I was on sabbatical at the Census Bureau. So this is a case study applied to the 2010 decennial census. These are results from the 2010 decennial census and merged numidant data or administrative data in the state of Wyoming. Here I'm looking at pairwise evaluation measures, which are computed using ground truth for a subset of the records. Here, the unadjusted published count by the census was this number here. According to our results under that have been released under the DRB that's listed on the first page of my slides, the pairwise precision and recall are 0.7 and 0.84 with an F1 of 0.9. And the posterior mean, you can see, has been adjusted. So roughly the overall error is about 10%, which I don't think is too surprising. And to my knowledge, we've calculated, I think, a posterior standard error for the first time. So next, I'd just like to briefly touch on the microclustering property and a little bit of work that we've done on this. So in terms of microclustering, we've found that with record linkage problems and entity resolution tasks, we end up having, if we look at this, we end up having small clusters with the data. So we don't ever end up with clusters that are quite large, which is something you see in Bayesian non-parametric models. However, a lot of Bayesian non-parametric models, such as infinite dimensional Bayesian non-parametric models, such as the Dirichlet process and the Pitt-Manure process, have been used a great deal in especially the computer science and machine learning literature, and have been applied to these types of applications. So one thing that I wrote in my NSF Career Award and have worked on in a collaboration with Zanella, Benacourt, and others, which has appeared in NIPS as well now in JASA, is just illustrating that infinite dimensional BNPs are often misspecified for ER tasks, defining theoretically what this microclustering property is, coming up with new models that fix the misspecification, and illustrating asymptotic properties of them, proving them, and then illustrating that they actually work on not just simulated data, but real data. And so this is still ongoing work, and something that I'm very interested in. If there's more questions on this, I'm happy to take this at the end of the talk. But I'll kind of leave the microclustering as kind of this for now. So you can see the misspecification in the sense that the DP is not able to recover these very small clusters, whereas the ESCD is able to capture all of them like just right spot on. And we see the same for the real data. So finally, what I'd like to end with are some case studies applied to human rights applications. So this has been a large focus of mine and something that I really enjoy doing. I think it's a very important thing to do. So one of the applications that I've worked on is a case study of the number of casualties in Syria. This is a very specific case study of a period of time from March 2011 to April 2014, where the goal was to see how well we were able to match results that were published by the Human Rights Data Analysis Group, HR DAG, which is led by Megan Price and Patrick Ball. We were able to find that our point estimate matched very closely, and we were able to find, to our knowledge, the first standard error of this. And so this appeared, this was joint work with Betty Chen, who was a PhD student at Rice at the time, and Anshamali Sharastava, and this appeared in the Applied Annals of Statistics. This work was also something that we did where we could run the algorithm in real time. And if I remember correctly, the code on the application, which had roughly 500,000 records, ran in roughly 300 seconds. So finally, I'd like to talk just about some current work that I'm doing with two of my PhD students. So one of them is a case study that's in El Salvador. So there was a human rights conflict in El Salvador, where victims were documented roughly between 1980 and 1992. And they were documented by different NGOs at the time. So some of the individuals were documented during the conflict and others were documented after the conflict. And so what we're doing here is we're comparing to the beta record linkage method, which was developed by Mauricio Sedinle in 2017. And we're proposing a faster version of this so that it can scale to much larger databases. So we're calling this Fable, and this is known as fast beta linkage. And this is being led by my PhD student, Brian Kundinger. And the goal of this here is to be able to apply this to very generalized real case studies. So we can see here that the posterior distributions are, we're underestimating the documented identifiable deaths. If we look at the point estimates, they're quite close to the ones that Mauricio came up with in 2017. The real advantage of what we're doing here is Brian just ran some things on the National Long-Term Care Survey. And so when he runs Fable, he's able to easily run that on something at 60,000 where the beta record linkage method isn't able to run. And so what we're doing is currently exploring how much we can scale, how fast we can scale, and how this might work for even larger applications. And so this is work that's also joint with Jerry Ryder at Duke, and this is in preparation. Some other work that I'm working on is with Olivier Bignette. He's a PhD student in the Department of Statistical Science, also at Duke University. And we've just recently submitted this last week. Here, we're doing case studies of all human trafficking data. This one I'm showcasing is in the UK, but we're specifically looking at all publicly available human trafficking data that does not have covariate information. And we've been looking at all of the commonly used methods that are used for population size estimation to try and give more guidance to the literature regarding which methods should be used, how they should be used, how sensitive they are in practice, how one can correct for particular biases and sensitivities. And so you can see just for the UK, the population size estimate is quite sensitive. Here's the point estimate, here's the credible interval. The range that was published is in the blue region. So you can see that, you know, if you're not quite paying attention, it's quite easy to perhaps tweak to the wrong value or towards a lower value, rather than you could also tweak to a higher value. And so again, our goal is to kind of give guidance to practitioners that are working in this area that may not be able to develop new statistical methodology. So with that, I'll end on that note. I'm happy to take questions regarding future thoughts about this area with growth. I've left my contact information, my webpage. If you're interested in learning more, I would highly recommend to look at this review article that Olivier and I have recently written. There's a lot of software my group has written, and there's an entity resolution tutorial that my entire group has put together. And finally, I just like to thank again the NSF, the Sloan Foundation, the Washington Statistical Society, NASS, and especially all of my collaborators and students, because it wouldn't be possible without them.
Excellent. Let's see, we do have 2 questions in the chat. So as host of this event, I'm going to rank here. And then afterwards, if you would raise your electronic hand so that we're not talking over each other to get the live questions answered. The first one is from Albert's son, who is an undergraduate student at Duke. And the question is, I was wondering if you could talk about the relationship between linkage matching strategy and fuzzy matching.
Is Albert still on?
Becca, would you like to move on to the next question? It does not look as if he's still here.
So it looks like Adeline asked a question regarding the 2020 census. I currently do not have access to the 2020 census data at this point. This is something I'm very interested in looking at. So specifically, I'm very interested in looking at a comparative analysis to the 2010 census and the 2020 census regarding, if you look at the case study that we've looked at in our JCGS paper, something quite similar. I can only talk about specific details that we published in the paper, given the confidentiality of the nature of the work that I've done. But it's too early to talk about successes and failures of the 2020 census. So I know everyone has lots of questions about that. But that's a great question. And I think it just needs more, in my mind, thoughtful analyses need to be done about these to make sure you're saying the right thing. And that takes a great deal of time and patience. So
I'll next open to the floor to David, and then we'll cycle back, Linda, to your question, and feel free to come off mute.
Oh, there's one question from Linda Young, actually.
Yes,
so Linda oh, sorry.
I was going to give Linda the opportunity to ask her question after.
Oh, sure,
David.
perfect.
Oh, go ahead, David.
Becca, that was lovely. You mentioned that in the human trafficking work you're doing with Olivier, you were only looking at cases where there were no covariates. But it seems to me the covariates are probably very important in that type of estimation. Why did you avoid covariates?
Oh, that's a great question. So we don't have access to the covariate data. And what we find is that what you can or cannot say regarding a population size estimate greatly differs if you have the covariate information or you don't have it. So I don't think this is very surprising, but the methods are, of course, much more sensitive and not robust to pretty much all of the methods when you do not have the covariate level information. And we're following up on some papers that have recently been published in JRSSA by Silverman and Whitehead and others. And I know you're familiar with those because you got me reading them. So we're trying to see something practical in those types of more difficult situations. I think it's much easier it's much easier to see something when you have the covariate information, but for these particular, for all of these specific situations, we actually don't have access to any of the covariate information. So specifically, Olivier has come up with some really nice new results on kind of going a bit further and trying to help practitioners and official statistics agencies of what they can and cannot do in these situations. Now, if they have the covariate information, you do something totally different. So.
Thank you.
Next, we'll go back to the chat with Linda's question.
I'm not sure how well my mic is working, is why I tend to put it in the chat. Okay.
You're good. You're good.
All right. So, Becca, have you worked much with establishment surveys? Would these methods extend readily to those? And especially, of course, I'm interested in farms, which might have complex structures with multiple LLCs within a farm. And sometimes we want to identify it at the LLC level and at other times at the overall enterprise level. How well would these methods work there?
That's a very good question. So we haven't applied the methods to something in that particular scenario. I would have to see the details more regarding the exact structure. They may have to be modified a bit. But I will say we haven't found an application we haven't been able to handle yet. So knock on wood. So we really like looking at complex things. So.
Well, we have a good one for you.
Sounds like this is quite a match here on some advancement in your research, Becca. Denise.
Yeah, hi, Rebecca. I work for Linda, and I kind of want to build on her question as well. I do feel that the complex structure of our files goes directly into your clustering structure. So I was wondering, if you ever get to take a look at one of our surveys, how will the clustering affect? Because one of the things that we run into consistently is extremely large clusters because of the complexity of the businesses.
How large are the clusters?
Well, let's just say pretty large, and then not just like 10 or 20 records. I mean, sometimes we get several hundred records because of the composition of the LLCs and the multiple operations.
So that wouldn't break that. So having a cluster with hundreds of records wouldn't break the framework.
Okay.
Maybe it was a bit misleading how I introduced the microclustering property, but one of the issues of using something like a Dirichlet process is the fact that it induces only large clusters. And so it never takes care of any of the small clusters. And so you just miss all of those.
Okay.
So we can still handle large clusters. It's just our framework also handles small clusters, which I assume you also have some small clusters.
Well, the small clusters, when the small clusters go through the clerical review, we're able to break them up. But when you have the large clusters, it's much more difficult to break it up during the clerical review, and that's where we encounter most of our concerns.
I would say the easiest thing to start with would be so the DeepLink package is all publicly available. So I would try that first, and then you could let me know how it goes. And that would be a starting point.
Okay, thank you.
There's a link to it on the slides. If you send me an email, I can also just point you to it.
Okay, great, thank you.
Sure.
Becca, we have another question in chat.
So there's a question regarding how would I suggest combining information about attributes of individuals with geographic proximity and entity resolution. I don't know so it really depends on the application. So you can use different things such as distance functions. You can use, it depends if you're thinking kind of like state proximity or spatial proximity, or I would need to know more information regarding the geographic proximity. But you could use something like a distance function, which is going to be more computationally intensive, but will be quite accurate. I mean, we already use location information. So when we're matching location and location, we do something like that. I don't know if Sigurd has a specific application in mind. So I will say everything is general, but then it does become application specific in terms of looking at the type of, what type of data you're looking at.
Becca, I'll throw out a question. To me, in listening to your talk, I was thinking kind of reverse video, the idea of we're not trying to match data, but we're trying to keep people from being able to match. So has this work been extended or adapted or used to assess disclosure risk, to make sure that the matching doesn't work well?
So that's a really good question. So there is a large literature that is known as privacy preserving record linkage. It's incredibly, in my mind, it's very misleading. Because if you think of trying to match people, if you're trying to find people and match people, that's the least private thing you can do. So if you think of a name of an algorithm called privacy preserving record linkage, it's really not, it's not two things that can go together. So typically what they do in this literature is they have a trusted third party that keeps attributes of the individuals and key information to try and keep the individuals private. And so it's a lot of theoretics or theoretical kind of proofs or something like that. But if I kind of think about how it works in an applied setting, To me, it doesn't seem very practical or real, because who is the trusted third party? Who would that be? So if I'm thinking maybe of, so if we're gonna just throw out something I talk with my students a lot about, if we're gonna think about doing vaccine passports, who's gonna be keeping all of our very private health information? Who's the gatekeeper? Is it, I mean, in the state of Wyoming, for example, they accidentally released all of the COVID testing information for an entire year on GitHub.
Okay.
So when I start thinking about, like even things that happen accidentally, I can't think of things that would make sense of like when we're thinking about storing health information on apps or trusted third parties or things like that. So to me, record linkage is not private. It should have ethical considerations. It has a lot of very nefarious uses. And at least in my own work and things I talk about with my students, we use it for ethical purposes. And we're very careful about what applications we work on and what we don't work on. So I think privacy preserving record linkage, this is my personal view, I think it's a bit of a pipe dream. So that's a great question.
I could see your methods, because in my line of work, we have certain data sets, public use data sets, where the sensitivity of the information, the PII is automatically not released, but there still is characteristics of, for example, individuals that could lend to disclosure of their identity. So
right.
Very, very interesting. Folks, we have a minute left. So I want to, again, Becca, this was fascinating. I have tons of other questions myself, which I'm sure we will interact in email. So I want to applaud you, and just briefly here to present you with an electronic award on behalf of the current past president, Eileen O'Brien, the incoming president, Mark Otto, and myself, Jill Deaver from the Washington Statistical Society. Thank you so much for your enlightening seminar. There will be more discussions, I'm sure, by the attendees here. So to let everyone know, we will be posting slides and video to the WSS website and the WSS YouTube channel. And this will facilitate more collaborations and much more dialogue. So again, Becca, congratulations. Thank you. This was beyond expectations, and we did set high expectations for you. So very much appreciated.
Thank you very much. Great honor. Thanks for the great questions.
So thanks everyone for attending today. Take care.